Hello? Okay. All right, you can hear me now? All right, let's go ahead and start. Am I recording? Okay. Welcome, everyone. So we'll continue our discussion about colors today. So now we're going to go into some water-soluble plant pigments. And these plant pigments that we're going to talk about belong to a really large family of compounds called phenolic compounds. And the general structure of phenol is shown there. So benzene ring with a hydroxyl group on it. And these compounds then would be antioxidant compounds. We often think about these compounds as some of the beneficial non-nutrient compounds that are found in plant foods. So there's a lot of them, again, but actually a lot of them don't really have any color. So we only talk about a few of them when we're talking about color. So the main one that we're going to talk about are the flavonoids, and you see where they are on this tree here. So this tree here would be flavonoids. And so their general structure would look like this. So here's that basic structure. We have two benzene rings connected with a propanoid group, a three-membered or three-carbon chain here. And so that would be the basic structure, but typically all of these flavonoids would then have some kind of substitutions on them. So the ones that we're going to talk about here would be anthocyanin. This is an anthocyanidin, but the anthocyanins. And that's because these are the ones that have the colors that we use, that we add to foods. So some of these do have some color, but they're not really commercially extracted and available. So mostly we have these anthocyanins. So when that oxygen has a positive charge on it, then that would be the flavillum cation. And then that oxygen at higher pHs will not be charged. And you'll lose this proton here and form a ketone right here. And so that's what will happen when that pH gets higher. I mentioned these are anthocyanins. And here this said this was anthocyanidins. So an anthocyanin is an anthocyanidin with a sugar attached somewhere. So you can have sugars attached at several places, at the 3 position, the 4 position, and even you can have them attached at other places as well. And that is how they occur in the plant, and even how they occur in a lot of natural color extracts. So typically we are going to be speaking about anthocyanins and not anthocyanidins with their sugars taken off. When the general term for when we take the sugar off would be an aglycone. So if the sugar is removed, we change anthocyanins to anthocyanidins, and we make an aglycone. So as I mentioned, at different pH values, we can have the cation version or the neutral version. And so in acid, we're going to have this, and it's going to be some shade of red. So we're talking here about red pigments, and a lot of foods that are red have anthocyanins in them. So very common pigments. If we raise the pH, then we'll get that ketone group like I mentioned here. So that proton will come off, will form this, and this oxygen here is not charged anymore. When we do that, the color changes. So this makes natural colors, especially anthocyanin natural colors, really hard to work with. Because if you take them out of their natural pH and put them in a food that's not at that same pH, a lot of times the color is totally different. So like, red cabbage would be something that is a very good source of anthocyanins and is also the source of a lot of anthocyanin extracts that are used for coloring foods. And in that red cabbage, if you increase the pH to neutral, then they're not red anymore. They will turn blue. The other two down there at the bottom are colorless compounds, so we can also actually lose the color. And these will typically happen at higher pHs. And you see some degradation here, ring opening, for instance. And so that would be, not desirable because those colors are not going to be able to go back to their original color. So the color changes are not very simple. So in general, anthocyanins will be red in acid and blue in base or in not acidic conditions. So like neutral pHs will be blue. And then as you increase the pH further, they will become colorless. So that's general. But some compounds, some anthocyanins will never turn blue. They just go from red to colorless. Or sometimes they'll go from red to colorless to blue. So it is specific to the type of anthocyanin. But most of them will go from red at acidic pH to blue at around neutral. And then if you go really high, they'll go colorless. So here's an example, like I mentioned with the red cabbage. Low pH, actually at really low pH, it's more red than you normally see because the cabbage itself is not that low of pH. So very red, and then it will go more to a purple color and then transition into that blue at around neutral pH. And then as you get to these higher pH values, those anthocyanins lose their color. So the question I wrote on there is, how do we get this green show up? Anyone have a thought about that? Well, what? It could be chlorophyll. It's probably other phenolic compounds. But that's exactly right. So it's just other colors. So the anthocyanins aren't turning green. It's just other colors are showing up. So in this case, the anthocyanins are actually losing their color. Okay, now here's a little, I guess, little quiz for us. So we want to understand the stability of anthocyanins. So let's see, I'll just do like a pen here. I never have very good luck with the pen. It never wants to show up unless I click on it twice. Okay. So relative stability to pH, heat, light, and oxygen. So in this first row, are anthocyanins going to be more stable in acidic pH or alkaline pH? Well, we already know the answer to that one, right? Which one is it? Acidic. Yep. Good. So, they're going to lose their color at alkaline pH, and then I even showed that we can open up those rings at alkaline pH, and so we get some degradation. So just like a lot of things that we've looked at, vitamins, minerals, all of those things, they like a slightly acidic pH. This is one here we haven't talked about. So we can have varying number of hydroxyl groups around those rings. So here, you can have all those positions can have hydroxyl groups on them, or none of them can have hydroxyl groups. So if we have more, is it going to be more stable or is it going to be less stable? Anyone want to guess? This is just a guess because we haven't talked about it yet. And you're right. So the more hydroxyl groups you have, actually, I'm sorry, the more you have, it's less stable. We're circling the more stable one. So less hydroxyl groups would be more stable. So, basically hydroxyl groups introduce opportunity for reactivity. And so they're a functional group that's reactive. And so if we have fewer of them, it will be less reactive and more stable. Okay, next is less or more methoxy groups. So I'll give you a big hint here. Methoxy groups are basically a protecting group for hydroxyl groups. So you put a methyl group on a hydroxyl group and basically make it not reactive anymore. So if you have more of those or less of those, which one's going to be more stable? More of them. Okay, and then last one, we can have no carbohydrates on there and have an anthocyanidin, or we can have lots of carbohydrates on there, 3 or 4. So if we have lots of carbohydrates on there, is it going to be more or less stable, do you think? So that's good if we think about hydroxyl groups being these reactive things. If we introduce sugars, perhaps they're more reactive. Actually, the more carbohydrate moieties you have, the more stable it is. So there's the answer, and make sure that you did not circle this one. So more stable at lower pH with less hydroxyl groups, and if you've got hydroxyl groups, the more methoxy groups or methyl groups are substituted on those, the better, and then more carbohydrate moieties will be more stable. Okay, here's another one. We're still looking at stability. So what's the stability as a function of water activity? So do we want a really high water activity, a moderate water activity, or very low water activity? So when the water activity is moderate, more stable. I have on here something between 0.63 to 0.79. It would be most stable. So that's fairly low. It isn't like pretzel low, but it's fairly low. So tying up some of that water, either with sugars or salts, and lowering that water activity, or just drying it out slightly, is going to improve the stability of these colors. Okay, what about sugars? So if we have a low sugar concentration versus a high sugar concentration, which one's more stable? Exactly. Mostly just because it lowers the water activity. So that first one sort of gave it away. But if we dump a bunch of sugar in there, like if we're making a heavy syrup, for instance, or even a jam or a jelly, lowering that water activity by adding a lot of solutes is going to increase the stability of those colors. When we have really, really low sugar concentrations, the individual sugars can differ in whether they're going to contribute more or less stability. So you don't need to worry about that. At those low concentrations, just know that each sugar will behave differently. So you can't really, I guess, predict it. But if we're just talking about total sugar, if we put a bunch of sugar in, it's going to be more stable, just mostly because of the lowering of the water activity. Okay, for metals, what do you think the effect of metals is? Just based on what you know about other stuff, what happens when you have these metals around? It's going to be less stable. So there are some exceptions. So calcium, iron, aluminum, and selenium complexes can be more stable. So in general, metals will decrease stability, but there are some metals that I listed here that can increase stability. So these metals, the ones that I list here, decrease stability of other pigments. That mostly the ones that we are going to talk about later. So tannins and stuff like that. So these complexes may increase stability of anthocyanins, but they may decrease stability of other compounds. Sulfur dioxide. So what do you think the effect of sulfur dioxide is? Is that going to improve stability of the color or not? Where have we seen sulfur dioxide used before? What? It's so hard to hear people with these masks on. We've seen it before drying apricots. Do you remember that? Do you remember why it was used? Preserve the color. Exactly. But those apricots are not colored with anthocyanins. So actually anthocyanins really don't like sulfur dioxide, so it's the opposite thing. So if we put sulfur dioxide with compounds that are colored with anthocyanins, then they will decrease, or it will actually remove all the color. So sulfur dioxide it will bleach anthocyanins, take away all of their color. So, really good example is maraschino cherries. You know those cherries you put on top of a ice cream sundae? So those cherries are colored with anthocyanins. If it's a berry, it's anthocyanins. So a cherry would be colored with anthocyanins. And when those maraschino cherries are processed, sulfur dioxide is used in that process. And it makes them white. And so if you look on the bottle for maraschino cherries, there's a bunch of red 40 in there to make them red again. So it will completely remove that color. Any of those berries, cranberries, anything like that will lose all of their color with sulfur dioxide. There's this, I hesitate to put this down because I don't necessarily expect you to remember it, but there is a special type of anthocyanin. If they're substituted at the C4 position with something to protect that area, they will be resistant to sulfur dioxide bleaching. So it is a little bit difficult to talk about these compounds in general terms because they are all very different from each other. And so just like I mentioned, some sugars will stabilize at low concentrations and some don't. And just like I mentioned that, some compounds, most of them go from red to blue, but some go from red to colorless. Here, some anthocyanins, specifically those substituted at the C4 position, are resistant to bleaching. During processing, anthocyanins will often lose their color, or at least change their color or decrease in intensity. But there are some cases where they will increase in their intensity. So anthocyanins can, during processing, dimerize and polymerize. And when that happens, the color changes, but it becomes, I would say, a richer color, darker color, a deeper color. So a good example is the difference between grape juice and red wine. So those are two different colors, grape juice being really purple and red wine being more red color. And that is because during that fermentation process, those anthocyanins that color the grapes can dimerize and polymerize and form these complexes with all sorts of stuff that's in there, and they become much more stable. So, those colors aren't going to be so susceptible to degradation as they were before, but they are also a different color, slightly different color. So these, now when they're polymerized like this, they are very much more stable to heat, to sulfur dioxide, to metals, to all of those things. Okay, anthocyanins, we can also introduce some organic acids onto the carbohydrate moiety on the anthocyanin. So I've shown here just an acetyl group here, esterified to the sugar residue on the anthocyanin. And these are called acylated anthocyanins. And it doesn't have to be an acetate group. It can be any number of organic acids here. But when we do this and add these acyl groups onto the sugar residue, it increases the stability of the anthocyanins. So you can see here in this graph, absorbance, that's going to be a measure of the intensity of the color and also the hue, or what the color looks like. So the dotted line here is unacylated, and you see here that it has a maximum absorbance of whatever, 490 or something like that. And this is how intense the color is. But when they are acylated with these different organic acids, you see a shift in the max absorbance, which means that the color that you see is a little bit different, but it is more intense. So the color is deeper, shifted a little bit, not totally unlike this shift here, but probably a little less of a shift. Okay, but there's more color. And then down here, this is a storage study. And actually, this is a storage study with maraschino cherries. And so here's the maraschino cherries colored with red 40, and the storage for 40 weeks there. And you see over time, the artificial color stays perfect. So that's what we would expect. But here are two acylated anthocyanins, and these are from radishes and red potatoes. And you see their color is changing over time. So we're losing some of that color during that storage time. But it's pretty good. Actually, the authors of this paper said, this is really great because there's really not a lot of change in color over time. So these acylated anthocyanins exhibit pretty good stability. You see that the intensity of the color is far lower than the red 40. So you see that the intensity and the stability and everything is much worse with these natural colors than they are compared to red 40. But as far as natural colors go, these acylated anthocyanins are much better to work with because they're a lot more stable, and both to processing and then after storage. So these acylated anthocyanins, they are naturally occurring. So it's not like we're putting those organic acids on there. And so now, all these steps we take to color something naturally are not natural anymore. So these are compounds that are naturally there. So the examples that I gave, radishes and red potatoes, they would have a good source of these acylated colors. There's several others that aren't shown on this slide. Red cabbage does have them, purple carrots, purple corn, sweet potatoes that are purple. Okay, next we're going to talk about anthoxanthins. So anthoxanthins are obviously a very similar kind of compound. You see the structure is not too different from the anthocyanins. These colors are white. Don't typically think about white as a color, but it is a color. So they are white, like in that cauliflower there, or they are like a light yellow color. So basically, these don't really exhibit much color at all that we would typically think of. But they are important to the properties of a lot of these compounds that contain them. So actually, these anthocyanins are in a lot of foods that that are green. So let's see. Broccoli, cucumbers, lettuce, green beans, spinach, parsley, celery. All of these things have a lot of anthocyanins, but they have a lot of chlorophyll. So that's all you really see is the chlorophyll. But they are, in the cauliflower there, and that's why it's white. They're in apples, and that's why the apples are white. So they are seen sometimes in some of these products. They're present, so the next one is procyanidins. Proanthocyanidins. And these are also, these are colorless compounds. So I did mention, remember, that these phenolic acids, a lot of them are colorless. So here's an example of one that's colorless. And you see, again, the structure very similar. But when we treat proanthocyanidins with heat in the presence of acid, they can convert to anthocyanins. And so those will have color. And so this example here, where you see this pink color, this is a pear, a piece of a pear. And so when we put pears in a can and heat process those, we have acid around, we have heat around, and we have metal around from the can. And so we can get those pears to turn pink if we're not careful. So when I was in college, I worked at a quality assurance lab. We did a lot of canned foods. And this was a main cause to reject lots of canned pears. And so, if the processing is not right, if it's too long, for instance, then those pears will definitely turn yellow or pink. And also, if there's any imperfections in the can, so those cans that you can the pears in, they have a lining in them that will protect the pears from reacting with the metal in the can. But if there's any imperfections in that lining, like scratches or nicks or anything like that, then those metals will react and you'll get that pink color showing up. The top picture there, that's a cocoa pod with the cocoa beans inside. So they have a lot of proanthocyanidins too. These compounds, proanthocyanidins, are very astringent. Anyone know what astringent means? Yeah, so that's really good. Removes, I would say. So it doesn't actually remove moisture, but it makes it seem like the moisture has been removed. So, some of you might see astringent or astringency on like your bottle of face soap or some kind of cosmetic, and that will tighten or make skin feel tighter or sometimes drier, not so oily. And so astringent compounds in foods, they cause like a puckering or a drying of the mouth. And so again, if you think about biting into an apple and that kind of drying out sensation that you get when you bite into that apple, and those are the proanthocyanidins. And if you take sensory class, then you'll learn about why that is. But anyway, astringency is a property of a lot of these phenolic compounds, and it makes it feel like your mouth just dried out, like the saliva is not doing its job anymore. Another class of compounds are tannins, and these tannins are also very astringent. Actually, I would say astringency is the main property of these tannins that you notice. So you see apple again there, having astringent compounds. There's two types of tannins. We have the proanthocyanidins, which we just talked about, and another name for those would be condensed tannins. And actually, the condensed tannins would be proanthocyanidins that are polymerized. And then we have hydrolyzable tannins. So here's our proanthocyanidin, and then you see that they're just hooked together, polymerized. And this bond here, what's this bond right here between these two anthocyanidins? There's nothing real special about this bond, right? It's just a covalent bond between two carbon molecules, or two carbon atoms. So let's look at these hydrolyzable tannins. These are very different, aren't they? So hydrolyzable tannins, this middle section here is a sugar, and all these things on the outside are phenolic acids. In this case, this is gallic acid on the outside here. So what's this bond here between the sugar and the gallic acid? This bond or this bond? It's a carboxylic acid and an alcohol condensed together. What is that? An ester. Esters are really, really not very stable, not very strong bond. So that's why we call these hydrolyzable tannins, because these ester linkages are really easy to break. So in acid, for instance, these can hydrolyze and we can break down these tannins. So after, say, a prolonged heat treatment or a fermentation or something that can break these kinds of bonds, compounds that are really high in hydrolyzable tannins can become less astringent. In contrast here, this bond we talked about, this is a very stable bond. This isn't going to hydrolyze. This whole compound is going to degrade before this bond breaks. So these compounds are not hydrolyzable. They are very stable. They'll just stay there forever till the whole thing breaks down. An important property of tannins is that they complex with proteins and polysaccharides, so biopolymers. So they stick to them. And that is basically why these compounds are so astringent. So I guess I was going to not tell you this, but when you eat these compounds, your saliva has proteins in it that give glycoproteins that give the saliva its slipperiness and lubricating ability. And one of the hypotheses, there's two really good hypotheses, but one of them says that tannins, when they come into your mouth, they complex with those glycoproteins in your saliva and make them not lubricate anymore. Either stick together and form large complexes, and that's why it feels really dry. So that is one property of them. So, this picture really is just to blow this up. Here's that ester linkage that's very susceptible to hydrolysis. And then here's this covalent bond that, there's nothing real special about it. It's not going to break down. The rest of this whole compound is much less stable than this bond right here. All right, we just have a couple more real short that we're going to go over. Betalins is the first one. So betalins, the real first thing that you would remember when we start talking about betalins are that they're from beets. So red beets get their color from betalins. And that is a very common place to extract red from those beets and then put it in a bottle so we can put it in food. The other really unique thing about betalins is that they have nitrogen in them. You see here, there's some nitrogen. And none of these other compounds that we've talked about in this whole section have nitrogen. So that's a unique property of betalins. Betalins can vary in their color from red to yellow. But usually we think about them as being red. Let me see here. Okay, so here is what happens when betalins are heated. So when we heat them, basically the bond between those two rings breaks. But what do you see on those arrows? It's reversible. So for instance, canned beets, that's a thing. A lot of us eat them that way very commonly. So actually, when you can beets, they become yellow. And then as they sit on the shelf, they turn red again. So part of the quality assurance measurement for these kinds of products is to allow them to sit for a period of time before you analyze the color to make sure that it has time to go back to the red color. Next, we have caramel color. So, this, I don't know if you want to classify this as a natural color or not. Caramel colors that you would purchase to include in foods to make them brown are produced by the same reactions that cause browning in baked goods, things like that. So they can be produced either from the caramelization reaction or the Maillard reaction. I think probably you've talked at least quickly about both of those reactions in previous classes. We will talk about them in more detail later. But they can be produced by those reactions with either degrading sugars to produce brown pigments or degrading sugars in the presence of some nitrogen-containing compound. So in foods, that nitrogen-containing compound is usually protein or amino acid. If we're making caramel color, that nitrogen-containing compound is usually just like ammonia. So I have here lists. I looked at this just the other day and I thought this isn't the best table. The rows, they don't mean anything. So this is just a list of 4 things. So it doesn't mean that the sucrose will react with sulfuric acid and ammonium. You know, you can do sucrose and sulfurous acid, for instance. But you can start with any number of sugars, and you can use any number of these acids. You can include some bases. You can include some salts. So, you know, those are all the different combinations that you can use to make these different colors. All of the caramel color that you would purchase to add to foods, they are all going to be a colloidal dispersion, a colloidal dispersion. So these brown pigments are large polymers, and so they're going to be just these dispersions rather than, you know, these small molecules that are coloring the material. They will have a very burnt flavor if you were to just eat them, but when we just add them, they'll be diluted out so that you won't detect that burnt flavor. There's 4 different classes here depending on the reactants that are used. So if we just use an acid or a base and a sugar, then that would be type 1. And then we can add more things. So if we include sulfites, type 2. If we include nitrogen salts, type 3. And then if we have both ammonium salts and sulfites, then it's type 4. And then you see the usage there. By far, most of these would be used in cola, beverages, and that would be that last one there, type 4. Titanium dioxide is a pigment for giving things a white color, whitening things. It is a mineral, naturally occurring. It is not soluble, has to be mixed with a suspending agent, either to be dispersed in water or oil. You know, could be some kind of polymer, could be starch, something that is going to help it suspend. And it's used in a lot of products just to make them look white. And then last, we have glossing agents. And these are just coatings that we can put on things to make them shiny. And they come from all sorts of sources, you know, from beeswax to, you know, insect secretions, all sorts of things that are used just to make these compounds shiny on the outside, mostly candies. And that's it. I think we're out of time, so that's good. So thanks, everyone. We'll go ahead and have our normal review on Friday. So if you've got questions or formulate some questions and bring them on Friday.